Hopefully you all feel good about the exam. I know some people finish quickly, others not as quickly. But I hope that you felt a little comfort and calmness about it. I had one student who I was chatting with who said that she and other students had been discussing the homework and that the homework was harder than the test questions and didn't really help them prepare. And now she's smiling and laughing about it. I do intend the homework problems to help you for the test. The homework problem should be at least a little bit harder than the test questions because you have, I allocate approximately 2 hours per class session for you to be studying, which I consider is primarily doing the homework and figuring out how to do the homework. So I consider about 2 hours for that, and that's only 5 questions. The exam, I actually figure the exam, you should be able to do everything you know in an hour, and then you have 2 hours to sit there and do the ones you don't know. So the question should be a little easier. But, if you're not getting something out of the homework, it is good to contact me and try to make it a learning experience, just like, the test should be a learning experience. That was a big arm right there. So that about the homework. Also, for the benefit of people at Southwestern, just before the exam, my students came up with the idea that they would appreciate having just a big old homework assignment that is extra credit due like the night before the exam. So it'd just be practice questions that they could do to enjoy. Okay, to me it'd be enjoy. But remember, I'm the guy who riding the bus to school and back was practicing math problems because I thought that was totally a thrill. So let us get on with the lecture. We're going to talk about rotational motion. The first 5 or so slides are slides you've already seen, including the first clicker questions, a slide you've already seen, a question you've already had, just to make sure we get back into the rotation. And we'll play with something like this, except for safety. We're going to be sitting down. We're not going to be standing up while we're doing that. So just review angular quantities versus linear quantities. When we have a rigid object rotating, we like to use angular quantities because everything in that rigid object is rotating with the same time to go around the circle. And so we define variables that have to do with going around the circle. So you have the angle that measures how far around you've gone the circle. We have the angular velocity, which is how much the angle is changing per time. And so angle here is related to the distance you traveled. S is the arc length, so S is the distance right there. Notice it's not a straight line because you're going in a circle. Is there a... That would be me hitting the wrong thing. Thank you for that verbal cue of... So that arc length is still a distance. So the angle is the distance you travel in the arc divided by the radius of the circle. And then the angular velocity, just like linear velocity is the change in displacement over change in time, the angular velocity is the change in angle divided by change in time. And just using the definition for the angle, you can put that into finding that the angular velocity is the tangential speed divided by the radius. Now, I had a student on the test ask about that tangential speed. Tangent is the direction that it's going at any moment. And so the tangential direction is constantly changing, but the tangential speed is how fast it's moving as it goes in a circle. And so that's why it has V sub t. Then that didn't do the right thing. Then we had the acceleration. I was just sending some instructions to Andrew. I don't know who Andrew is, but I'm sure he's a good guy. And talking about the last homework problem, and the very last portion of the last homework problem asks you to find the tangential acceleration, I think it is it asks you to find, the angular acceleration. And you have calculated your initial, you were given initial angular velocity and you calculated final angular velocity. So all you had to do there was to use this relationship that the angular acceleration is the change in angular velocity divided by the change in time. Just like linear acceleration was the change in velocity divided by the change in time. And then this here is just substituting the omega we had from the previous page to show that the angular acceleration is equal to the tangential acceleration divided by radius. And then a final thing, centripetal toward the center. The centripetal acceleration is the acceleration necessary to keep something going in a circle. How do we use centripetal acceleration? We use it when we're using Newton's second law. We say the sum of the forces toward the center is equal to the mass times the acceleration toward the center. On that same homework problem, it has you make a free body diagram of what's going on with a yo-yo hanging from a string, swinging around a circle. Well, when you make a free body diagram, what forces do you show on the free body diagram? All the forces that are acting on the object of interest. So in that problem, your object of interest was the yo-yo. So what forces would be acting on a yo-yo? I don't have a yo-yo here, but close enough. Actually, I do have a yo-yo. Still going to use this. So I have it out like here. It's going in a circle, so I'm holding it out here with my hand because it's not going in a circle. What forces, if my thumb's not here, what forces would be acting on that bob? Tension. What direction does tension always point? The direction of the rope leaving the object. So you have that direction. What other forces do I have? Gravity. What direction is that always? Down, by definition. That's the end. Why don't I have centripetal force acting on it? Because centripetal force is a sum. This right here is the definition of centripetal force. It's what you get when you add up all of the force vectors that were on your free body diagram in the direction toward the center. It's not a force that shows up on the free body diagram because it's not a force acting on the object. It's the sum of forces acting on the object in a specific direction. So that diagram should only have the two forces that are actually acting on the yo-yo. Okay, going further with our review slides, our kinematic equations. I only wrote here one kinematic equation, the one that we use the largest percentage of the time because it has all the variables. We have a relationship between position. Position is equal to the angle times the radius. Remember, that was arc length, is the angle subtended times the radius. And likewise, the speed is the angular velocity times the radius. The acceleration is the angular acceleration times radius. So I can take these and just substitute them in. So I'll put x, replace it with a theta r, v, replace it with omega r, and a, replace it with alpha r. And so you can see the line below, I've done those replacements. That kinematic equation still has to be correct. And so when you do those replacements, you notice that it just has an r in each term. So I divide that r away. The radius isn't going to be 0 because we actually have something moving. I assume it's not 0. And so as long as r is not 0, you can legally divide it away. And you get this for your new kinematic equation for rotation. It looks exactly the same as we had before. It's simply we've changed from the linear to the rotational variables. Now, this is just one of the kinematic equations, but how do you suppose a kinematic equation like how would that equation change if I substituted in my rotational variables? What would V final become? Omega final times radius, right? So I have that squared minus V initial is omega initial times radius equals 2. The acceleration will be the angular acceleration times radius times theta final times radius minus theta initial times radius. Now I have r squared. I forgot to put a square there. R squared, r times r, so r squared again. I just have r squareds everywhere, cancel the r squareds, and again, the equation looks just like the linear equation, except for you change to the rotational variables. So what's the point of this? Doing kinematic equations for rotation is exactly like doing kinematic equations that we've done before. It's just you've changed the names of the variables from the linear name to the rotational name. So now our first clicker question, which was our last clicker question last class period, I believe. Which components of linear motion are related to components of rotational motion? And while people are answering, I'll just make a statement here. I sent an email to actually 5 students at Southwestern who haven't logged into their clicker account through Moodle yet. One person did log in through Moodle. Now it's giving me scores where it wasn't before. The other 4, I can see that there are 4 accounts that have been answering that I can't tell who they are. Hence, when you log in through Moodle, I will be able to get scores, but until then, I can't get scores for your clicker participation. So I sent emails. You 4 people know who you are. Just want to make sure it's clear. Okay, about 5 more seconds. Okay, and I'm actually not going to ask anyone because we've already, whoops, that was the wrong number. 13 was down here. So there's our answers. I'm not going to ask somebody, put them on the spot on this one. I'm just going to move forward. It was the tangentials. That's why we had the subscript T. The tangential velocities relate to the rotational motion. The centripetal, I did have the centripetal in one place, but it's not a direct relation. It's, because it's going in circle, you have to have an acceleration that depends on the centripetal acceleration that depends on the the rotational velocity. Okay, a second question, one that we didn't have before. When using the rotational forms of the kinematic equations, the ones that we just looked at, what units should you use for angle? And you'll note that I didn't talk about angle when we were there. So this is asking a question out of the blue. And so you're going to have to reason your way through. And this person here is going to defend his answer. Or maybe not, because it looks like that person's not here. Okay, give it 5 more seconds. Oh, good. Person is here. All right. So this time we only had 2 answers. And I am going to ask Robert Dominguez to give your answer and explain your reasoning.
I went with B, radians.
Okay.
I did that because that what you usually use in such a case.
Okay. That's what we use. Okay, I forgot the word we. All right, that's good enough. We use radians, but you know what? We can also use degrees. And if we can use radians or degrees, we can use any units. If we look back at the equations here, there is one angle in each term here. That is, I am currently looking at this equation, one angle in each term there. So that means the unit you use for angle, if you use the same unit in every variable, is just going to cancel out in the end. Likewise, for the second one I did, there's angle squared in each term, right? Alpha times theta, that's going to have angle squared. And so again, the angle units are going to cancel out. So it turns out that the correct, all of these are correct. It doesn't matter what angle you use as long as you use the same one throughout. Now, just to make sure we're clear on these terms, cycles is complete circles. Degrees are dividing that circle into 360. Gradients, I put gradients there because when I got my first calculator, now you guys have to remember, I didn't see a calculator until I was like third grade, right? They started these little slide rules for training us to use slide rules like in first grade. And then calculators came out and that all went away. So I didn't actually learn how to use the slide rule. But I got a calculator when I was like a freshman in high school because, it was a pricey thing back then. And it had 3 units for angle, degrees, gradients, and radians. And of course, we use degrees and radians. And so I was like, what in the world is these gradients? I have to learn about it. And the gradients is basically saying, well, 360 degrees is useful, but wouldn't it be more useful to be able to break up a quadrant into 100 instead of 90 degrees? And so the gradients is just 400. And I don't even know a symbol for gradients other than grad. 400 gradients is a complete circle. As far as I know, the only people who use this to any extent at all are engineers. So it's not something that you're going to have to worry about. We're not going to use it in physics class, but it's a simple unit. And then radians, you have 2 pi radians in a circle. Of all of these, the radians are a unitless degree. There's actually no unit when we say units of radians. If we say units of degrees, it's a conversion factor, and you can figure out your conversion factors just from those numbers. 1 cycle equals 360 degrees equals 2 pi radians. I'm not going to put gradients here because we're never going to use it. And so you can get your conversion factor just by using that relationship. No matter what angle units you have, you can always convert between them in a simple way. And of course, the one we usually relate is these two here. So 360 degrees divided by 2 pi radians is equal to 1. So that's 180 degrees per pi radian. And so there's the conversion factor that you usually use. All right, so a simple kinematic problem, and then we're going to start talking about things that I find a lot more fun. A wheel is subjected to a constant angular acceleration to go from 123 RPMs to 321 RPMs in 5.75 seconds. Number one, what's the angular acceleration of the wheel? First thing we have to do if we're going to solve this is say, what's an RPM? Okay, so RPM, 1 RPM is equal to 1 rotation per minute. I can go ahead and calculate my angular acceleration in units of rotations per something. But you know what I like to do? I like to convert at least to, per second. And given that part 2 asks how many cycles does it go through, I'm going to leave it in revolutions because 1 revolution is 1 cycle. I didn't specify what units to use for number 1, so cycles per second squared is acceptable. If I asked you to put it in standard units, you would put it in radians per second squared. Homework problems should specify what units you're going to use. So you have to pay attention. So the first thing I'm going to do is convert, by the way, 123 RPMs. It doesn't tell us what that quantity is. If it's rotations per minute, what type of quantity is an RPM? It's a what?
Scalar.
Okay, it is scalar. It's scalar because they didn't give us direction. Got to give you credit there. Technically, there is a direction to it. It's just they didn't give it to us. But just look at the units, rotations per minute. What type of unit is that?
Speed.
If it was a speed, it would have been a distance, like meters per minute.
Angular speed.
It's an angular speed. Angular speed because we don't have direction. So I have my omega initial is equal to 123 revolutions per minute. And then I want to convert that to revolutions per second because I want to get into seconds. So I just have to look at, this is per minute. Let me change where it says RPM to putting, well, revolution, cycle per minute. And I want to get this in terms of per second. So I'm going to need to put seconds on the bottom. In my conversion factor, what do I need to have on top? I need to have minutes, so I'll have 1 minute, as one student said. And how many seconds are in 1 minute? We all know 60. And so 123 cycles per minute divided by 60 seconds is going to be, what, 20.5 cycles per second?
2.05.
2.05. Excellent math. At least I got the numbers in the right order. Forgot that there was a 0 in the bottom there. So that's my initial angular velocity. My final angular velocity is 321 cycles per minute times, again, 1 minute per 60 seconds is equal to
5.35.
So now notice I use cycles. It started by saying rotations or revolutions. Does it matter? No, they mean the same thing. I could have put RPS, revolutions per second. It would have been fine unit. Now to find my angular acceleration, just like I said, the last homework problem from the last assignment, you just take the change in angular velocity divided by the change in time. Notice I'm not using hertz. Hertz is actually an abbreviation that means cycles per second. But when you're talking about angular velocity, you tend to not use that term. You use it for other situations. And the time given was 5.75 seconds. That one there is not amenable to my brain.
0.5739 rotations per second squared.
Now, how many significant digits do I actually have in this problem? Yep, just had to come up and check myself. So the correct answer to correct significant digits would be 0.574 cycles per second squared. So that's my answer for the first one. The second one, how many cycles does the wheel go through during this acceleration? If I ask you how many cycles does it go through, which variable am I looking for?
Theta final.
I'm looking for the change in angle, the change in theta. So theta final minus theta initial. Of course, let's just set theta initial equals 0. We'll find theta final. So then I just take my kinematic equation that is going to relate time, my initial speed, and my angular acceleration. I'll be good. Or I could have said, well, if it's a constant angular acceleration, then I could say, well, and a number of people did this on the test, my average angular velocity is the sum of the two divided by 2. Now, oddly, a number of people on the test said the average was the final minus initial divided by 2. I actually saw enough times I went and double checked that I didn't have it wrong in the equation sheet. But the average is the sum of the two. So I'm going to do it this way because a number of people did this on the first exam, except for, of course, it was speed then. So that would be so that's 7.40 divided by 2, 3.7. So I can say that's my average angular velocity. And so what was the time? It's 5.75. And so that would be one way to get the answer.
21.275.
And of course, to 3 significant digits, that's 21.3 cycles. That's one way of doing it. The other way of doing it, the way that I would have been more prone to do, would have been to use the equation delta theta is equal to the initial angular velocity multiplied by time plus 1/2 the angular acceleration that we just found multiplied by time squared. Either method would have worked. They would have given you the same answer. So when you solve a problem like this, as Rachel told me, there's more than one way to skin a cat. And unlike in her anatomy and physiology class, they're both right. Because apparently the teacher there said, there's more than one way to skin the cat, but there's only one right way, and this is it. And I thought that was kind of gross having to skin a cat, just for the record. Okay, now we're going to turn to things that are more interesting. We've talked about torque. Remember my dad's definition, a very apt definition. It's the amount of twist, or make it a little more correct, it's the rotational equivalent of force. It's the twisting force. It's not a force, it's the rotational equivalent to force. And torques and angular momentum are tightly related. Angular momentum, well, let's back up and talk about momentum, linear momentum. Linear momentum was related to inertia. What is the measurement of inertia? I think somebody said mass. That would be the correct answer. Mass is the measurement of inertia. So you could look at me and say, man, Webb's got a lot of inertia, right? It sounds better that way, doesn't it? And the inertia is telling you about how much nature wants you to stay in the same motion. And then we had momentum, that was your motion, the velocity, multiplied by your inertia, the mass. If we go to rotational or angular momentum, we're going to do the same thing, but we're going to take your rotational equivalent to velocity. What do we call your rotational equivalent to velocity? Angular velocity. Take your angular velocity and multiply that to your rotational equivalent to inertia, mass. So it sounds really goofy to most people. Say, what, the rotational equivalent to mass? Like my mass isn't the same thing if I'm rotating as if I'm going straight? And for rotational purposes, that's a correct statement. It's not the same. So the equation for angular momentum, first the symbol, L is angular momentum. And just like linear momentum, it's telling you about how much motion you have and how hard it's going to be to stop. So it's the velocity times the inertia idea. It's a vector, so you should put a vector sign over it if you're going to be all technical until you say, well, this is the magnitude, and don't. So angular momentum is L vector. And to calculate it, we have it's equal to the angular velocity vector multiplied by the rotational equivalent to mass, which we call the moment of inertia. Or we can call it the rotational inertia. There are a few other names you can use for it. It's the rotational equivalent to mass. Now, we have some engineering students. What do you guys refer to it as? What words do you use? Or have you not talked about it yet? Yeah, okay. Because they talk about it like, I think, the second moment or something like that. They have slightly different words. So what makes up that rotational equivalent? You can go through and do calculations about, using linear equations in a rotational system, but I'm just going to go straight to the chase. The moment of inertia is equal to the sum of each little piece of mass multiplied by the perpendicular distance between the axis of rotation and that mass squared. So if I take this picture here of this skater, her axis of rotation is pretty simple. It's just going to be a vertical line. Well, that's vertical. Trust me. It's a vertical line like that. And so that R is going to be the distance perpendicular to that to any point. So if I take her chin, there's the R perpendicular for her chin. It's perpendicular to the axis. If I take her knee, the R perpendicular to the knee is that. And so you have to take each little piece of mass and its perpendicular distance from the axis of rotation, and you square the radius, multiply it by the mass, you add them all up. Oh, calculus, physics 251 students. If we have something like this person, the only way we could possibly do it would be to integrate over the person. And of course, we're not going to integrate over a person because it's way too complicated, right? Because the density is changing in different locations and, it's way too complicated. For people who are in general physics, that's most of you, what do we do? Most things are not point masses. If I had a point mass, if I, for instance, could say, well, this mass is a point mass, or being better, this is more realistic to that ideal. This bob I can treat as a point mass if the distance from where it's rotating to where the bob is large compared to the radius of the object. Treat it like it's a point. And so for this, I'd say, well, that's easy. The radius is the length of the string, and the mass is the mass of the bob. And so I just take the mass of the bob times the radius squared. And so my moment of inertia for this going around circle is just mass times radius squared. Or if I have a wheel, imagine that the spokes on this have negligible mass. I have all of the mass out here at the radius. It's all the same radius. So when I add it all up together, it's just going to be mass times radius squared. But what if it's not all out there at the edge? Something like this has the mass pretty uniform, not perfectly uniformly. You can see it's got cutouts, but the mass is pretty uniformly distributed from the center out. Well, then we use calculus. If you're in the non-calculus class, which once again, most of you are, you look it up in a table. So like on the test, I'll give you the values or have a table. You'll either have a value in a problem or I'll give you the table so you can look up and identify. So what does that table look like? Well, not like this. Not like that either. Darn it. I've got the table here. There. So here's the table. It has a number of different objects. And notice you have the same object here appears 4 times. Why 4 times? Because it can rotate about different axes. So the first one is about the center of the cylinder. When it says cylinder axis, it means the line going straight down the center of the cylinder. And so in that case, it's 1/2 mass times radius squared. So a hoop was mass times radius squared. The cylinder is 1/2 mass times radius squared. That was a question that was in the concept coach questions. A student asked me about it. Why are they different? Because in one case, the mass is all at R away. In one, it's distributed throughout. And doing the calculus, it turns out that it's 1/2. This one over here is if it's rotating about the central diameter. So that is, it's rotating like this. The distance from the mass to the axis going through the center here is completely different than the distance from this axis. And so you have a completely different outcome. And so you have 1/4 mass times radius squared plus 1/12 mass times the length squared. This one below it is rotating about this axis. Farther away now, instead of at the center, it's at the edge. And then the final one here is a thin rod through the center, perpendicular to the length. Actually, wait, Oh, this one here is thin. This one here does not have thin. That's what's different. So the radius term just went to 0 here because it said it's thin, so the radius is negligible. So that's the difference in those two. Then notice for the sphere, we have rotating about a center axis. This is a spherical shell rotating about that same axis. You just look up what you have and calculate. Okay, going back to where we were. The direction of angular velocity is found using the same right-hand rule that we learned before. So right-hand rule for angular velocity, wrap your fingers the direction that it's rotating about an axis of your right hand. Your thumb points the direction we assign the rotation to. So if I have this can rotating like this, then its axis is vertical axis. I wrap my fingers the direction it's going. My thumb points up. So rotating like this is up. Rotating like this is down. That's how we get the directions, just using that right-hand rule. So we've seen it. Angular momentum, since it is a vector that is in the same direction, you can't see vector signs here because they use bold. I'll put vector signs because the bold to me doesn't stand out very well. The angular momentum is in the same direction as the angular velocity. Now our clicker question, which is actually pretty straightforward. What direction is the angular momentum of the second hand of the clock? So your options are going into the clock face. That would be, in the case of the clock in the classroom, going into the wall here. Or coming out of the clock face, coming out of the wall to the top of the clock, bottom of the clock, left and right. Okay, another 6 seconds or so. All right, we had fairly strong agreement here. And so the card that I just drew is Benjamin St. John. I heard I picked A because.
Oh, because I was kind of picturing it in my head.
Okay, so he's picturing his head, and that's the way that made sense. Well, the way to get the answer and make sure you're always right, because I mean, sometimes you picture your head and you are right. When problems get more complicated, it's harder to try to picture your head to get the right answer, and that's when you need to rely on, other methods. So if I take my right hand, not the left, but the right, and I wrap my fingers in the direction that the second hand is moving, clockwise clearly, I go like that, and my thumb points into the wall. Hence, you chose the right answer. Your thinking was correct, Benjamin, that it's going into the clock face using the right hand rule. Now, we've already talked about the right side of this slide. The left side of this slide is basically all of our equations for rotational dynamics. We have, this is a linear equation, kinetic energy, and we're going to start talking about this as the translational kinetic energy now. Translational means the motion of the center of mass. So the motion of the center of mass of something is 1/2 the mass times the speed of the center mass squared. And then we'll talk about the rotational kinetic energy, the kinetic energy of mass rotating around the center of mass. And that rotational kinetic energy is, well, of course, it still needs to be 1/2 mass times speed squared for every little piece of mass that's going around that center of mass. And so once again, doing math that's not overly exciting, you just replace V with omega R. it would be 1/2 mass times radius squared times omega squared. I forgot to square the omega here. My mistake. I made another mistake. Yeah. No, that's good. That's correct. And so this here would apply to each little piece of mass. If you add all the pieces up, you have kinetic energy rotation is 1/2 moment of inertia times omega squared. And so that's the equation that we're going to use for the rotational kinetic energy. So I think these were actually on the equation sheet for the test we just did. The rotational kinetic energy is 1/2 I omega squared. I is the rotational equivalent to mass. Omega is the rotational equivalent to speed. So it's the same as the translational, just changing from the translational variables to the rotational equivalents. So we have kinetic energy in two different ways. Then angular momentum. No. There's an equation in the middle that's not the one I showed you. I showed you angular momentum was I omega, the moment of inertia times the angular velocity. But here we see it's R cross P. What does that cross mean? Cross product, we're multiplying the perpendicular parts of the radius and the angular velocity. So it's a cross product, and torque we've already learned is R cross F, again multiplying the perpendicular parts. Newton's second law, this one here of course is another linear equation. The rotational equivalent to Newton's second law, you just replace force with the rotational equivalent of force, which is torque, mass times the rotational equivalent of mass, which is moment of inertia, and acceleration by the rotational equivalent, angular acceleration. So that's what this is. And then the second part is we can replace momentum with the rotational equivalent of momentum. So the net torque is moment of inertia times alpha. Notice that's not the torque equals. It's the net torque equals I alpha, which is equal to I, moment of inertia, times delta L. What is L again? Angular momentum over delta T. Now I'm going to, work. If we calculate work, we know that work is equal to force dot the motion. I'm going to use delta S here because it has S. So force parallel times delta S. If I actually apply this to a rotating object, that's going to be equal to change delta S to delta theta times R. But the force and the radius are always perpendicular. And so that's equal to the torque times theta. So for rotational variables, the work is the torque applied times the angle that it rotates through, which is once again just replacing linear variables with angular. Now for some fun, we have kinetic energy and rotation. People have tried things like spin up a wheel and use that to drive a vehicle. You do that to some extent already. Your vehicle has a flywheel. Depending on your vehicle, it might have a bigger or smaller moment of inertia. The idea is your engine is going bang, 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 and so you have jolts pushing on the crankshaft. Well, you put this flywheel, and that flywheel has a certain angular momentum, well, not angular momentum, moment of inertia, resistance to change in motion. So if you make the flywheel so it has a bigger moment of inertia, it's not going to jerk as much each time a piston fires. If it has a smaller moment of inertia, it will. Also has to do with acceleration some. I drive my car, I press on the gas and not much happens. My sister used to have a Boxster and I was amazed, like even in neutral, I press on the gas and the car doesn't rev as fast in my car as it did in her Boxster. They used a smaller flywheel so that you could get the engine spinning faster, quicker. Okay, so let's do our little demonstration. We're going to do a race between the cans. I bought these 2 cans when I came to Union College. So one expires in 2005 and one expires in 2004. We're going to race these 2. I'm not going to eat these soups, I decided, even though I spent my own personal cash on them. So I'm going to race them down this ramp. And the question is, which of these cans is going to win the race? And you can start answering now. So which can is going to win the race? Will they tie? Will it be the chunky soup or will it be the creamy tomato soup? I'm not going to call on somebody to defend their answer on this one. This is your prediction just based on your gut feeling for the most part. Okay, about 5 more seconds here. And we had 22, 17, and 12. So they weren't all the same, but there was fair disagreement. So we do the experiment. After all, we're scientists here, right? Right. So for the experiment, I put both of these on here, separate them so they won't crash into each other, hopefully. And the one closer to you is the creamy tomato. The one farther from you is the chunky soup. Ready? Yeah, it's so exciting. Drum roll. The winner was creamy tomato. Loser, chunky. Now, I always do this multiple times just to make sure it wasn't something like I let it go wrong. So I'm going to switch the position. So now the tomato is going to be closer to me. And do it a second time. Hopefully get them going straight down. And the winner was, again, tomato. Tomato won. So 17 of you had the right answer. Now, of course, having the right answer, that's not really the goal, right? And on the test, that's good for 1 point, assuming you have some reason for it. Knowing why, that's the whole rest of the ball. So the question here is why. And I have a clicker question. We're just not going to do it on why. Instead, I'm going to explain it because we only have 3 minutes. So why did one win? Why did the creamy win? What's going on? Let's talk about energy for today. What's going on in terms of energy from when it starts to when it ends? What kind of energy does it have at the start? Okay, it has gravitational potential energy. What kind of energy does it have at the end? That kinetic energy is broken up into 2 pieces. The kinetic energy of translation, the center of mass cruising down, and the rotational kinetic energy. So the potential energy initial is mass times gravity times whatever this height is. The kinetic energy final is going to be 1/2, that's a 2, the mass times the final velocity squared, plus 1/2 the moment of inertia times omega final squared. There is a relationship between omega final and V final. That is, we learned that V is equal to omega R, or omega is equal to V over R. So I'm going to make a substitution here. 1/2 M V final squared plus 1/2 I times V over R quantity squared. Now factoring out the 1/2 V final squared times M plus I over R squared. So the final kinetic energy is 1/2 the mass times, 1/2 the final speed squared times the mass plus I over R squared. The moments of inertia, these are the same mass. It actually wouldn't matter if they were the same mass, because if you look across the equation, I'm going to have my mgh that I start with equals this. So the mass actually is going to cancel out because moment of inertia depends on mass too. They have the same mass, but when they spin, the mass is going to be distributed differently. The chunky soup is uniform, so the mass will remain uniform throughout. So not the chunky, the tomato soup. Tomato soup is uniform, so for the tomato soup, it's going to be like a solid cylinder, so it'd be 1/2 mass times radius squared. For the chunky soup, you have things of different densities. And when it rotates, what's going to happen to material based on density? The more dense stuff is going to go to the outside, the less dense to the inside. So let's take the bold approximation that all of the mass goes to the exterior. We know that's not the case, but it's in that direction. So moment of inertia for the chunky soup is closer to mass times radius squared. So that means this term here is larger for the chunky soup. And because that's larger, then the speed is going to have to be slower. Whereas the tomato soup had a smaller moment of inertia, so it could have a higher speed to have the same final energy. So the bottom line is the chunky soup had more energy in rotation, which meant less translational energy, which meant slower speed. The tomato soup had a lower moment of inertia, less energy in rotation, which meant more into the translation. Okay, we're out of time, so we'll do the other two next class period. Did my sound get better over there at Southwestern, or is it still garbled?
It's still heavy.
Okay.